7,000 years ago, the ice sheet of Antarctica was smaller, and scientists think they know why. This is by Dan Laurie and Holly Keir from The Conversation. As the climate warms and Antarctica's glaciers and ice sheets melt, the resulting rise in sea level has the potential to displace hundreds of millions of people around the world by the end of this century. A key uncertainty in how much and how fast the seas will rise lies in whether currently stable parts of West Antarctica ice sheet can become unstable. One such region is West Antarctica's simple coast, where rivers of ice flow off the continent and drain into the ocean, and we know that there are a lot of underground volcanoes under the ice sheet there. Antarctica has over 140 volcanoes. Now, this ice flow is slowed by the Ross Ice Shelf, a floating mass of ice nearly the size of Spain, which holds back the land-based ice. Compared to other ice shelves in western Antarctica, the Ross Ice Shelf has little melting at its base because the ocean below is very cold. Although this region has been stable during the past few decades, recent research suggests that this was not always the case. Radiocarbon dating of sediments from beneath the ice sheet tells us that it retreated hundreds of kilometers from 7,000 years ago and then advanced again to its present position within the last 2,000 years. Figuring out why this happened can help us better predict how the ice sheet will change in the future. In our new research, we test two main hypotheses. Testing scenarios. Scientists have considered two possible explanations for this past ice sheet retreat and advance. The first is related to the Earth's crust below the ice sheet. As an ice sheet shrinks, the change in ice mass causes the Earth's crust to slowly uplift in response. At the same time, counterintuitively, the sea level drops near the ice because of a weakening of the gravitational attraction between the ice sheet and the ocean water. As the ice sheet thinned and retreated since the last ice age, crustal uplift and the fall in sea level in the region may have regrounded floating ice, causing ice sheet advance. The other hypothesis is that the ice sheet behavior may be due to the changes in the ocean. When the surface of the ocean freezes, forming sea ice, it expels salt into the water layers below. This cold, briny water is heavier and mixes deep into the ocean, including under the Ross Ice Shelf. This blocks warm ocean currents from melting the ice. Seafloor sediments and ice cores tell us that this deep mixing was weaker in the past when the ice sheet was retreating, and this means that warm ocean currents may have flowed underneath the ice shelf and melted the ice. Mixing increased with the ice sheet and was advancing. We test these two ideas with computer model simulations of ice sheet flow and Earth's crustal and sea surface responses to changes in the ice sheet with varying ocean temperature. Because the rate of crustal uplift depends on the viscosity and the stickiness of the underlying mantle, we ran simulations within ranges estimated for West Antarctica. A stickier mantle means slower crustal uplift as the ice sheet thins. The simulations that best matched geological records had a stickier mantle and a warmer ocean as the ice sheet retreated, and in these simulations the ice sheet retreated more quickly as the ocean warms. When the ocean cools, the simulated ice sheet re-advances to its present-day position. This means that changes in ocean temperature best explain the past ice sheet behavior, but the rate of crustal uplift also affects how sensitive the ice sheet is to the ocean. What this means for climate policy today. Much attention has been paid to recent studies that show glacial melting may be irreversible in some parts of Western Antarctica, such as the Amundsen Sea embayment. In the context of such studies, policy debates hinge on whether we should focus on adapting to rising seas rather than cutting greenhouse or gas emissions. If the sea ice is already melting, are we too late for mitigation? Our studies suggest it is premature to give up on mitigation. Global climate models run under high emissions scenarios show less sea ice formation and deep sea mixing. This could lead to the same cold to warm ocean switch that caused extensive ice sheet retreat thousands of years ago. For West Antarctica's simple coast, it's better if we prevent this ocean warming from occurring in the first place, which is still possible if we choose a low emissions future. And this article was republished from a conversation under Creative Commons. This is by Dan Lowry, Ice Sheet and Climate Modeler, GNS Science, and Holly Kiro Han, and a NASA postdoctorate fellow at NASA on Science Alert. Please leave your comments. Thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.